Καλησπέρα everyone, I'm Christos Aridas and I work at Sadways. At Sadways, we build solutions across sectors like civil protection, public safety, critical infrastructure and defense, smart cities, and Industry 4. My role focuses on taking AI from research all the way into production. Today I will show you how you can bring clarity to our data science workflows by moving into a more structured way of working. So let's start with a familiar situation. First, we are not sure which dataset version went into the analysis. And afterwards, you are staring at the model's directory and you are wondering what the final model really is. So these numbers might look good, but without knowing which dataset or model produced them, they can't be trusted. So this is where pipelines really help. In its simplest form, a pipeline is a process that takes code, configured data, and produces outputs or artifacts like models, plots, and metrics. But if you zoom in, a pipeline is a sequence of interdependent steps where the output of a step becomes the input of the next one. So each step is connected, and that structure makes the whole process easier to repeat and reason about. Thank you. So with a structured pipeline, reproducibility tells us that if we run the same experiment again under the same conditions, we should get the same results. So there are several reasons that we should care about reproducibility. Because if we can repeat our work, we can make steady improvements. We need a fair baseline to see if a new idea is really better. We should know how the data turned into a model step by step. Sharing makes it easier to work together and stay clear. And in fields like finance or healthcare, we must show exactly how results were made. Reproducibility can break in many ways, so I will list the common causes and how to control them. At first, differences in systems can give different results. So by using containerization technologies, we can control them and everyone runs in the same setup. Second, libraries and packages change over time, so we can use package managers in order to pin them so we stay consistent. Third, some algorithms have randomness built-in, so setting seeds make the results repeatable. Fourth, even small changes in parameters can change the outcomes. So storing them in config files keeps pipelines and experiments consistent. Fifth, we have the human factor. Manual steps often lead to mistakes. So automating the workflow reduces the errors. And of course, the data itself can change or go missing. Versioning datasets so experiments can always be produced is a solution to this problem. And thus brings us to DVC. With DVC, your team can collaborate on data and models the same way you already do with code. You can track every version of datasets and models and roll back at any time. You can run with DVC, compare and organize experiments. Also, DVC provides us an automated pipeline framework ready to use out of the box. It works with Python, with R or any other stack that you use, and it connects to whatever storage you use. So features are nice, but better see them in action. For today, I have prepared two examples. One example with data versioning and one example with pipeline management experiment tracking. So the first example uses a dataset of okras, bamyes in Greek. People tend to either love them or hate them, but for our use case, it doesn't matter. The dataset is public, so you can try it by yourself. So let's see how this okra dataset is organized on disk. I will use a tree command, and as you can see, we have a classic multi-class dataset with one folder for each class. So we start by initializing a Git repository with git init. And if we perform git status, we can see that our project is empty, except from the data directory, which Git doesn't track yet. So then we initialize DVC in the same project, and DVC sets up its own configuration inside this repo. So performing git status, we can see the configuration file, git ignore at DVC ignore, which is an echo event for Git for DVC. So now we can commit and start versioning the data the same way we version code. So in order to start track our data directory, we perform a DVC add data. So DVC collects all files in the folder and calculates unique hashes for versioning. Once DVC finishes, it creates a special data.dvc file describing the data. It is a metadata file. So Git can now track this metadata without storing the actual dataset. So the raw data itself is ignored by Git. Instead, GitD tracks the new metadata file, and DVC uses the file to track the actual data. So as we can see in the git ignore file, DVC added the data directory, preventing huge file from being committed to our Git repository. So all DVC tracked info, like hashes and file counts, is stored in this special data.dvc metadata file. So Git only sees this small metadata file and not the actual files. DVC keeps the actual data in a cache organized by hash. This makes storage efficient and avoids duplicates. Inside the hash folder that we saw earlier, DVC stores the real files mapped to their relative paths. So that is how it knows which file belongs to which state. Finally, we commit the changes to Git. So the dataset itself stays out of Git but is fully versioned by DVC. So in order to share or to backup our data, we have to configure a DVC remote where the DVC will send the data. So here it's a local folder for simplicity. So after the command, DVC knows how and where to push and pull the datasets from. Of course, we commit the configuration to Git and perform a DVC push, so the DVC uploads the actual dataset to the remote storage. So after the DVC push executes, all files are now safely stored in the remote separate from Git repository. So let's now merge the overmature class into a mature class for simplicity. So now we have just two directories, mature and other mature. So DVC should track the changes automatically. So performing a DVC status shows that the data has changed since last commit. So we commit the updated dataset to DVC, creating a new version that keeping the Git clean. So Git status will show the changes in metadata file data.dvc. Like this. So finally, we commit the metadata to Git, but please note that the actual data itself is versioned by DVC and not Git. So now, what if we want to go back to the original dataset? To restore the original dataset, we check the get history to find the commit where it was first added. Performing a git log, we find the hash. So we restore the .dvc file from that commit. Please note that this operation updates just the metadata file and not the actual files. Running a DVC checkout updates our workspace to match the restored .dvc file. So DVC fetches the correct version of the dataset from the cache. So now the folder structure is back to the original three classes. Performing a git commit, we have now the restored version of the data. So now let's switch to a classic tabular dataset, which is called Titanic. As you can see, our code is modularized into separate modules, where each module performs each a stage of the pipeline. So our pipeline is clear and maintainable. We define experiment parameters in a file params.yaml. For example, the test size, the random seed, and a hyperparameters. Here is new neighbors. So this keeps experiments reproducible and easy to tweak. Here we create a DVC stage to split the data. We specify its dependencies, outputs, and parameters, so DVC can track it automatically. All other stages define a similar way, so forming a complete pipeline. DVC generates a dvc.yaml file that lists each pipeline stage, including its commands, dependencies, outputs, and parameters. It's a clear record of the pipeline that can be tracked with Git. With DVC DAG, we can visualize all the stages and their dependencies. And another version of DVC DAG, we can see the output files instead of the dependencies. So this can help us to track artifacts across stages of the pipeline. So we run experiments with DVC exprun. So DVC automatically determines which stage you need to run based on changes. We will see the pipeline progressively executing all the stages. So like this. DVCXPSO displays all experiments, including the master branch and the current workspace. This makes it easy to compare results at a glance without digging through logs. So let's see what happens if we run the experiment without change anything. Everything was skipped. This saves time and guarantees reproducibility. But what is really happening? DVC creates a special file to capture the state of the pipeline. The dvc.log file stores exact hashes of all dependencies, outputs, and parameters. This is how DVC ensures that reruns are predictable and fully reproducible. When we run DVCXPSO, we see a new entry for the experiment, even though all its stages were skipped. We can tweak parameters directly from the command line, for instance, changing a hyperparameter like new neighbors. DVC only reruns the stages affected by the change, skipping everything else. So this is efficient and ensures the results reflect only the intended modification. For instance, split stage and preprocess stage skipped, while the train stage and evaluate stage run. DVC metrics let us see how metrics change between experiments. So we immediately know if our hyperparameter adjustment improved performance. Now, when we combine DVC with CI/CD, every change in Git can automatically trigger the DVC pipeline. This keeps our workflows up to date, reproducible, and fully tracked without any manual steps. So first, what DVC is. It is a tool for versioning data and models, letting you track them like just you track your code. It's a system for reproducible pipelines and experiment management, letting you keep track of every step and experiment. It's a tool for collaboration and sharing in data science projects, so your team can work together more easily. And what DVC isn't. It is not a replacement for MLflow and weights and biases dashboards. It's also not a database. DVC doesn't replace storage systems for querying or managing huge datasets directly. And finally, DVC isn't a full one-click MLOps platform. It gives you the building blocks for reproducibility and pipeline management, but you still need to integrate with other tools for end-to-end MLOps. So in short, DVC gives you the foundation for reproducible and collaborative data science, without pretending to do everything for you. So start your net project right, version your data, track your experiments, and make it reproducible with DVC. Thank you.